So in this video, we are going to look at thermodynamics. I want to focus on one particular topic, molar heat capacity. Now, I'm going to teach you or explain to you what molar heat capacity is all about, the definition, the formulas in what, if the formula in what, in calculating molar heat capacity. Then we are going to look at two main type of molar heat capacity, and that is where going to be our major focus. Molar heat capacity at constant volume, and molar heat capacity at constant pressure. Now, we have to look at how they are being derived formulas. Then we have to look at the relationship between the two of them, relationship between CV and CP. Molar heat capacity at constant volume and molar heat capacity at constant pressure. Just at their relationship. Not only that, we want to look at how to solve various problems on this particular topic. So you want to stick to the end of this video. If you see find issues with this topic, then this is your lucky video that will make to understand everything about this topic. So make sure you don't miss out. So now let's look at the first thing. What is molar heat capacity? So please take it down, take the definition down. By heat capacity of a system will mean the capacity to absorb heat and store energy. As the system absorbs heat, it goes into the kinetic motion of the atoms and molecules contained in that system. This increased kinetic energy raises the temperature of the system. So if Q calories is the heat absorbed by mass M and the temperature raised from T1 to T2, the heat capacity C is given by the expression. So now look at something here. So now molar capacity is the ability of the system to absorb it and store it as energy. Do you understand? So that when calculating molar capacity, there are three things you need to put in mind: the Q, which is what the quantity of heat absorbed; the mass of that system, which is what the mole of the system; then the temperature. Now there's going to be what change temperature. So here you can see that C is equal to Q over N change what in T. Just an N change T. Now, where N is what is the mole of that system. Just an N is what? N is the mole of the system. Q is what is quantity of heat absorbed. You understand? Then change T. Change in T is going to be what? T2 minus T1. Do you understand? So here we say C equals to what? Q over what? N T2 over what? T minus 2 what? T1. So this is the formula for what? For heat capacity or molar heat capacity. Now, let's assume that, now because if you want to solve this kind of problem here, you assume N to be what? 1. That is, the mole of the system is always 1. Do you understand? So can you just say let N equals to what? Of 1. If N is equal to 1, then here we have C equals to Q over change what in T, right? Now most times you data T can be data T. Most times it can also be like C equals to what Q over change what in T. Two of them are the same thing here. Just have two of them are what are the same thing. So where C means the heat capacity, Q means what quantity of heat, then this one here means what change what the T means what change what in T. Do you understand? So yeah, you can that the molar capacity of the system is defined as the amount of heat required to raise the temperature of one mole of the system by 1 Kelvin. Since the heat capacity can vary with temperature, its true value will be given as, so the true value of delta C is going to be C equals to what change the Q about change the T. So this is what main formula for what heat capacity. Do you understand? This is what formula for what heat what capacity. Thus, molar heat capacity may be defined as the ratio of the amount of heat absorbed to raise in temperature. So now look at what. Remember, I told that here is what? Here is N, right? But we assume to be what? To be 1, N to be 1. So what is the unit of what? Of heat capacity or molar capacity? Now you have what? Q is what is heat, right? Is the quantity of heat absorbed. So it's going to be what? And it is measured in what? In joules or calories. Joules or calories. I get over this n here is what is mole. So here we can say mole times this one is what is temperature, which you can which measure what in Kelvin. So now it means that we have two units of what heat capacity. So let's look at what units of heat capacity units. So it can either be joules per mole per Kelvin. Is it okay? Joules per mole per Kelvin or calories per mole per what per Kelvin. So please take note of this one here. Most time it can be in joules per mole per Kelvin. Most time it can be what calories per mole per Kelvin, depending on the one Kelvin to you. Do you understand? So the next one to look at is what is the heat capacity. So so the next one to look at is heat capacity at constant volume. So let's look at what heat capacity at constant volume. So let's look at what molar heat capacity at constant volume. So now when we talk about molar heat capacity at constant volume, now I want to give you a derivation. So pay close attention. So molar heat at constant volume. Remember, now we talk about change in internal energy. Now we have done change in what internal energy, right? In change in internal energy, we have a formula that what change in E is equal to what Q plus W, right? Now, but when I talk about internal energy of a system, now remember there are two ways in which what work can be done in the system. So what can be done by the system or what can be done on the system. So it can be either be expansion or compression. So this is formula. This is your general formula for what internal energy. Change your internal energy. Change internal energy equals to what Q plus W. Where this change is what change internal energy. Q is what is the heat absorbed or involved. Then W is what is the work done. Now, this work done can either be expansion or compression. Now, if you are talking about heat capacity at constant volume here, the work we're actually looking at is called expansion work done. That is work done by system. And whenever work is done by system, W is always what negative. Right there. So now, because of for the sake of this derivation here, work is done by the what system. And when work is done by system, the formula we are going to make is of this what is change what E equals to what Q minus what W. So this is what formula we are using here. This formula you are seeing here is what work done on the system. Why is called what work done by the system. So this is the what formula we are making use of. So from here now, we want to what make this Q the subject of formula because we are talking about what it's right. So that because here we have change, so here can just say change E equals to what change Q minus what minus W. Now another thing we want to understand here is that W is equals to what P change what volume here. It's called pressure volume work. I have done a complete video on that. That was my second video. If you have not watched that second video where I explain how to calculate question using this formula and this formula here, then I will link the link at the description below or you see it here. So by the end of this video here, make sure you go watch that video here because there are so many things I talk about in that video. The basic calculation, you understand the basic calculation, then how to solve problem using those formulas. So these are stuff you likely see in the exam. So go check out that video here. So now remember here we have W equals to what P change V, right? So now if you should impute this value here, like this formula here, I want to have change E equals to what? Q of change Q minus P change V. Do you understand? So from here, this is what general formula here, but here we have positive here. Now, whenever you have the positive in this formula here is what is called compression. Work is done on the system. Now, but whenever work is done by the system, we have what negative. Whenever you are deriving any formula here, we are assuming that work is always done by the system. That's why here is what negative, right? So because there is change here, let me put change here, right? Now, W is equal to P change volume. So you have it here. Now, the goal here is that let's make this guy the same formula, change the Q. Because now, the reason why I'm making change Q same formula, we are talking about what? Its capacity. So, because we are talking about capacity, let this guy be, let's do some big, Let's make this guy solve the formula here. If you make this guy subject of the formula, you have change Q is equal to what? E change E plus P change V. This that. Now, whenever you are deriving here, you always what divide through by change in what temperature. So you can say divide through by change in what temperature. So that change in temperature is what change in T, right? So which was the T. So if you divide both sides by change in temperature, you have change in Q over change in T. Can you see that? Change in Q over what change in T equals to what? Change in E plus change in PV over what? Change in T. Now, remember we are talking about at constant volume, right? At constant volume. Now, when you talk about at constant volume, what should be your mind? At constant volume, we are talking about isochoric process. Now, I'll talk about this thermodynamics basic concepts. That is the first video I produced. Thermodynamics basic process. What is thermodynamics? What is system? What is boundary? What is surrounding? And different type of process. We have what we call external, isobaric, isochoric, cyclic process. Now, when I talk about at constant volume, what do you mean at constant volume? Now, at constant volume, guys, you're talking about at constant, there is change what in V, right? You're talking about change in V is equals to what? 0. That is V2 equals to what? V1. That is there's no change what in volume. And whenever there is no change in volume, now whenever there's no change in volume, then you're talking about at constant volume. That is the implication here is that work is always what? 0. You get so at constant volume, change V is what? It's 0. Okay, so if you place 0 here, now if you place 0 here, so here we are change in Q or change in T, right? Equals to here we have change in E plus P0 or change in T. Because that here will turn to 0, right? So what do you have here? Here we have change in Q or change in T equals to what? Change in E or change in T. Can you see that? Now, because we're talking about at constant volume, right? So can you please play like at constant volume? At constant volume. Can you see that? Now, but understand that what is heat capacity? Heat capacity is the ratio of what change what it's is the ratio of what change what point of heat over what the what change what in temperature, right? So because C is equal to what change in Q or change in T, right? So if you place it here, you can say C V equals to what change in E or change in T. That's that. So the heat capacity at constant volume is equal to what? Change internal energy over what? Change what in temperature. So this is not the formula. This is what the formula for what? Molar heat capacity at constant volume. Now, if you should what? Make delta E the subject of formula. So you're going to get delta E is equal to what? CV change in T. You get. Now, remember, we're talking about for 1 mole of a gas, right? For 1 mole of a gas. But what about for n mole of a gas? When they say the mole is 2 mole, 3 mole, 4 moles, now or 1.5 or 1.6, depending on any mole given to you. I'm not going to use this formula here. That change E is equal to what? NCV change T. So this is now what the formula. You understand? So this is what I'm going to make use of in your calculation. So this formula here is what heat capacity at constant volume, which is what change the internal energy over what change what in time. And if you make change internal energy to a formula, this is what I'm going to get. Now, but this what you're seeing here is what is for 1 mole of a gas. What about for n mole of a gas? When the numbers of moles they give it to you, maybe you have 2 moles or 3 moles or 1.5 moles. So going to be change equals to n change V times what change what temperature. So this is what you're now going to what make use of. So this we call heat capacity at constant volume. Just and so now look at what heat capacity at what constant pressure. But molar heat capacity at constant pressure. What is the formula for molar heat capacity at constant pressure? Now it will do me no harm for me to what just give the formula here, but I want to show you how it's being derived. because as a student you must know how this formula are be derived. Do you understand? So now we are starting with this guy here. Change your internal energy equals to what? Q, change Q minus change P change V, right? So when remember this formula here that we use in what? At constant what? Volume, right? We are still going to apply the same thing here. Do you understand? Now, if I should make this guy the subject of formula here, yeah, I would have change Q equals what? Change E plus P change V. Do you understand? So this thing is very, very what important. Now I want to use this guy along with what? One formula. Now that formula is what? Enthalpy of a system. The enthalpy of a system is always equal to the internal energy plus pressure, volume, work. Now these are the two things we are going to look at. This is called enthalpy. This enthalpy is what? Is it at constant, is it at constant what? Pressure. Do you understand? So because this guy you are seeing here, H you are saying what? Change Q at constant what? Pressure. This is what you want to know. So these are the two things you are going to what? Make use of in this formula. We now want deriving heat capacity at constant pressure. This one here and this guy here, the two of them are what? Related. So now let me look at this one. Look at this guy first. So remember, here we have change Q equals to what? Change E plus P change V, right? Divide both sides by what? Change T. Just that. Now when divide both sides by change T, you have to have change Q or change T equals to what? Change E or change T plus P change V or change T. Remember, change Q over change T is what? Is the heat capacity, right? So in the previous one here, you can just replace C. That is the heat capacity is equals to what? Change E or change T plus P V change what? T. Do you understand? Now that is for this one here. Now let's bring out this guy. So if you bring out this guy, H equals to what? E plus P V P V. Now let's introduce our changes. If you introduce our changes here, we are going to change what? Enthalpy. Enthalpy about change enthalpy. Change enthalpy is equals to what? Change enthalpy equals to what? Change the what? Internal energy plus P change what? In volume. Very important here. Do you understand? Now let's divide both sides by what? Change what? Temperature. If you divide both sides by change temperature, here we have change H what? Change T is equals to what? Change E what? Change T plus P V change V what? Change what? In T. Now at look at something here. At constant pressure, at constant pressure, here you can say at constant pressure, nothing will be affected. You understand? So it's going to be change H or change T pressure equals to change E or change T plus P V change T pressure. Can you see that? Now if you relate this guy and this guy, they are what? Related. Do you understand? Now the other of this guy is this one here, and C is equals to this. Understand this here? The other of this one you are seeing here is this one here, right? And C is equals to this guy. So what you want to do here? Let me wipe this place out. It means that change in enthalpy over change the temperature is equals to. Now instead of me in places one here, because the of this one here is also the same type of as heat capacity, right? So it's going to be Cp. Can you see that? So Cp is also what? The change in internal energy over what? Change in what? Temperature. Very important. Do you understand? So if you check it very well, Cv and Cp are similar or related. Now, let me explain to you so you understand. So now here we have Cv. Now what is CV? Change your internal energy or change the time, change your temperature, right? Now we also have what we call heat capacity at constant pressure. We will CP because we will change your enthalpy or change the time. So because our two of them are related. So now when I talk about heat capacity at constant volume, is what you're talking about internal energy. Now when I talk about heat capacity at constant pressure, you're talking about enthalpy. You get. So now if you should what make this guy a formula here, which is going to be delta E equals to what CV change T, right? This formula is what for 1 mole of a gas. Now, for numbers of gases, if you have if you have mole of a gas, if the mole is not one, so the formula you want to make use of is delta E equals to NCV change T. Very important here. The same use of that one here. If you want to make enthalpy the sorry formula here, you're going to be change H equals to what CP change T, right? For n mole of a gas, when the mass of mole is being given to you, right? You make the what change H equals to what NCP change time, change what temperature. Very important. So there are the what two key formulas you are going to use when it comes to molar heat capacity, CV and what CP. And I've taught you how to what to derive this formula. They are very what easy. In case you don't know how to derive this formula, just understand these two formulas here. You understand? In order for you to what able to what solve problem yourself. Do you understand? So the next thing we want to look at is what is the relationship between CP and what CV, because this is very important. Look at what the relationship between CP and what CP and CV. Now, what are the relationship? Now, we are going to use three key formulas which I have already established already. Now, remember, CV is going to change in internal energy or change temperature, right? And CP goes to what change in enthalpy or change in what temperature, right? Now, I will know that enthalpy is equal to what is enthalpy equals to internal energy plus PV, right? Now, let's introduce something. Let's introduce something here. Now, remember when I have this guy here, this one here, this one is what if you look at the ideal gas equation, Now, in ideal gas equation, here we have PV equals to what nRT, right? N what RT. Now we are talking about what for n mole of a gas, right? So we are going to ignore this n. So for n equals to 1, for n mole of a gas, here we have PV equals to what R what T, right? Do you understand? So anywhere I see my PV, I put what ROT. So let me introduce here. So going to be H equals to what E plus P plus what? Now instead of putting PV here, I put what ROT. So going to be what ROT. Do you see that? Now remember, whenever you are deriving any formula here, you need to what divide by what change the temperature, right? So now let's introduce our change here. So going to be change what in enthalpy equals what change what in internal energy plus arrow change what in temperature. Do you understand? So we are going to introduce what our change. So the change going to affect this temperature, not our here. Do you understand? Now remember, we are dividing both sides by what change temperature. So if you divide through by change temperature, so going to be divide through by change T. If you divide through by change T, here we have change H or change T is equals to what change E or change T. Can you see that? Plus arrow change T or what change T. Before that, this guy cancel out this one here. Then if you check our definition here, changing H or changing T is what heat capacity at constant what heat capacity at constant pressure. So now instead of placing this one here, going to be CP equals to the same thing with this guy here. Change over change T is what is this one here. So which what CV. So going to be CV plus R. So the relationship between CP and CV. So the relationship between CP and CV is what? CP equals what? CV plus what? R. Very important. So R can either be in what? In joules or in what? In calories. So we have two different units in what? When it comes to what? R. R means what? Gas constant, right? So it will be R here equals what? 8.314 joules per mole per Kelvin. Or R equals what? 1.987 calories per mole per Kelvin. Just now, so you have what technical this one here. So what are the formulas we have derived in this video? In this video, we have derived that CV equals what change E about change T, right? And we later define that change E equals what NCV change T. Very important. We later define CP equals what change H about change T, right? So later we define that change H equals what NCP change T, right? Now, we also derive what the relation between, so we also derive from here H equals to what E plus PV, very important. Then the last one we derive is what is CP equals to what CV plus what R, very important. So these are the 1, 2, 3 formula. 1, 2, 3, 4. These are the what 4 formulas we are using in calculating question under this topic. So pay close attention there. So that let me talk to the calculation aspects. Okay, now let's look at what the first calculation. Let's look at what the first calculation is. That 4.5 mole of hydrogen gas in a container of volume of 20 dm3 and at a temperature of what 27 degrees centigrade was heated to 65 degrees centigrade and the volume changed to what 38.5 dm3. The heat of the heat capacity of the gas at constant volume is this. So what they ask to calculate is what change internal energy or what change enthalpy. So let's look at what the data given to us. They give us mole. Mole equals to what 4.5 moles, right? Now you can see that we have what we call V1, V2, T1, T2, right? My V1 and T1. My V1 is what 20 dm3. My T1 is what 27 degrees centigrade. Is okay. Remember, we always convert what degrees centigrade to what to Kelvin. So if you convert degrees centigrade to Kelvin by adding 273, so 27 plus 273 is what 300. So you have 27 plus 273 equals to what 300 Kelvin. Very important. The same thing here. My V2 is what? My V2 is 38.5 dm3. My T2 is what? Is 65 degrees centigrade. Now, if I should add 273, 65 plus 273 is what? 338 Kelvin. Do you see that? Now, they want to give what? Heat capacity at constant volume, which is what CV, to be what? To be 20.1 joules per mole per Kelvin. Very important. Just now, they're asking us to calculate change internal energy and what change enthalpy. This is what they say. This is what they're asking us to look for. So I want to write this place here because we don't need this. Change in internal energy because what NCV change T, right? So yeah, you can easily calculate what change internal energy. So here we have change E equals to what? My N is what? My N is what 4.5. So you're going to be 4.5 times CV, which is heat capacity at constant volume, which is 20.1 times my temperature going to be T2 minus T1, right? So now when I see change in temperature, dt equals to T2 minus T1. Just that. So now my T2 is what? 338 minus T1 is what? T1 is what? 300, right? So what will be the answer? So you have 4.5 times 20.1 times 338 minus 300. So you have change internal energy, which is 347.1. The unit is what? Joules. Just that. Now, how do we get joules? Now, let's go about unit analysis. analysis. It's okay. Now change internal energy because what? My N is what is mole, right? Times my my heat capacity at constant volume is what? What is unit? Joules per mole per Kelvin. So here you can say joules per mole per Kelvin times, right? Now T is what is T is what temperature. Temperature is what is Kelvin. You find that mole we cancel out mole, temperature we cancel out temperature. So that's why we have joules. Just and that is why it is what is joules. So my change internal energy is what 3437.1 joules. Because also as well convert to what to Kelvin, right? We convert to now we can convert to what to kilojoules because as well convert to kilojoules. If we convert to kilojoules, here we have 3.4371 kilojoules. Just like the same here, right? Now let's calculate what enthalpy. Now because this one for the internal what energy. So let's calculate for the enthalpy. But change in H is equal to what? NCP change what? Temperature. Now, but the problem here is that we are not giving CP, right? But we know that CP equals to what? R plus, we know that CP equals to what? CV plus what? R, right? So that is the relation between CP and what? CV. Now remember, since we are talking about joules, remember R is what is constant, gas constant. So going to be R here equals to 8.314 joules per mole per Kelvin, right? So remember CV is what? CV is 20.1 joules per mole per Kelvin. So my CPM is very easy. Add two of them. So it will be 20.1 plus 8.314. So if you should add two of them, 20.1 plus 8.314, you will have 28.414 joules per mole per Kelvin, right? So now let me pick our value now. Change your H equals what? My N is what? 4.5. 4.5 times my CP is what? 28.414 times my change in temperature, which is what? 338 minus 300, right? So you have 4.5 times 28.414 times 238 minus 300. So you have change H is equals to 4858.794. So the answer is what is joules. So that is the answer. You get. So this is how to solve problem on this one here. So I will drop two questions on the boards for you to try. You get. This is the same process. It's not that difficult. Your take home, your assignment. So you try your best and solve this one for me. Do you get that? So you can leave your answer in the comment section. I will respond to that. Let me see what you can do with the knowledge I'll give to you. Now here we have gram here, right? But for the question, for the one I use mole. It means that you are going to convert this gram to mole. And mole goes of mass, what molar mass. Like they say oxygen gas. Oxygen gas is what is O2. So I have to calculate molar mass for this guy. Just same thing with our the other one here. So what I want to do here, please look at the question and try to solve it. So we are done with what? Molar heat capacity at constant volume and at constant pressure. So believe me, you're going to see this type of questions in the exam. So if you still have a question in the exam, it should be a bonus mark for you or a bonus question. Do you understand? So in the next video, we have to take to the higher step. But we have two first video I've done here, the basis of what thermodynamics and the basic what calculation. So you can go check two of them out if you have not watched those videos. See you in my next video.